Moving on to our last derivative rule, this one is going to enable us to differentiate, that means to take the derivative of a composite function, which hopefully you see at the top, hopefully you learned in Algebra 2 and or relearned in pre-calculus. But a composite function, you basically think about it as like a function inception. It's a function plugged in within another function. So you see stuff like f of g of x, fog. That's another way of writing f of g of x, right? You take that whole entire g function and you plug it in to f, or you could have GOF or FOF or GOG, right? Function composites shouldn't really be new. If it is, definitely go YouTube it, go Khan Academy it, go check it out. I'm not going to have time to reteach you all the algebra. I just want to do the calculus. So we have these plane functions or these parent functions, and we know how to take the derivatives of them. But how do we work with these more complicated functions? Like here, this composite function, you could break it down into the two layers. You have the outer framework, which is taking something and raising it to the 7th power. And then you also have the inside piece, which is the 3x squared plus 5. So recognizing that that function is a composite, the outer framework is you have something getting raised to the 7th power, then your inner piece is that inside something. Same thing for this middle example. Your outer framework is sine of stuff, and then your inner stuff, the inner piece of the composite, is 4x. And then also we could do this last one. Now if you need to, you could rewrite this as just cosine of x cubed, right? Cosine cubed, that's the same thing as cosine of x all cubed. So here the outer framework is you've got something getting cubed, and then the inner function, right, is the thing that's getting cubed. So the inner function is the cosine. So recognizing when I have a composite is going to be key, because when you recognize it, then you're going to remember to do chain rule. And chain rule is an easier rule than the product or than the quotient rule that we saw in the last video. But this one's harder because it's sneaky like a ninja. It's just harder to see and it's harder to remember to do. If you remember to do it, you will probably do it correctly because it's not a hard rule, but it's just sneaky in the fact that you may miss it and you may forget to do it. So recognizing something as a composite, a function within a function, as opposed to just a regular old plain parent function, that's going to be crucial. So make sure your pre-cal skills are good, make sure your algebra 2 skills are good, make sure you know what a composite is, and then how to recognize it. But let's go forward. Here's the derivative rule written out. I'm going to rewrite it like this in a slightly different way, right? So if you have a composite, so if you have f of g of x, so your outer function is f of something, all right, that's your outside framework, and then your inside piece is your g of x. So if you have this composite, you have an outside and an inside, basically both pieces are going to be accounted for, right? The outer function is going to change. It's going to have a derivative, and that inner function is going to change. And so here we have to account for both of them changing, but we kind of do one of them at a time. Here's how I'm going to write it out with f primes and g primes. When I have a composite, I have f of something, and then the inside piece is g of x. The first thing you do is the derivative of the outside. So I'd have f prime of, and then whatever was inside of your original function, so whatever that stuff was, that goes inside of the derivative. So you're going to have f prime of g of x, and then you're going to multiply it by the derivative of that inside piece, so times g prime. So basically, if you want to put it in terms of words, you would say it's the derivative of the outside times the derivative of the inside. Be really careful. It is not f prime g prime. You don't do all of the derivatives at once and then squish them together. You are going to do all of the derivatives. Like I find the derivative of the outside, then I find the derivative of the inside, but I find all of those individual derivatives and I'm going to multiply them together. Right, so let's go back and let's revisit those three at the top, and let's see what these derivatives would be, noticing that I have an outside and an inside for each piece. So taking the derivative, I need the derivative of the outside times the derivative inside. Again, let's go back up here. So here, if your outside function is something to the 7th power, I know the derivative would be 7 something to the 6th, right? We know that's the power rule. Exponent multiplies to the front, decreases by 1. Now what's important is whatever was inside getting raised to the 7th, that stuff stays the same, and it's going to be that exact same piece now getting raised to the 6th power. So here on the inside, I'm just going to copy. Right? And so right now I've accounted for the outer layer. I had something to the 7th power. The derivative is 7 something to the 6th. I still have to account for this inside piece. It has a derivative, and I'm going to take its derivative. And let's see, that derivative would just be 6x. And I'm just going to multiply by that derivative. Right? The 6x does not go in here. Whatever was getting raised to the 7th, that exact same thing, you just copy it, is on the inside, right? That inside piece stays the same. You account for that inside's derivative by multiplying by it. So you have the derivative of the outside. If you had something to the 7th power, it'd be 7 something to the 6th. Then you multiply by the derivative of the inside. So you basically just identify all the layers of the composite, take the derivative of each one, and then you just multiply them all together. Let's go for the next one. Here I have sine of something, and I know the derivative of sine is cosine, right? And then I think, okay, what goes inside the parentheses? Well, whatever was inside of the sine is now going to be inside of its derivative. So that was sine of 4x. So that inside piece stays the same for now. I know 4x is a function. It changes values, right? It has a rate of change. And I need to account for this guy's derivative, and I would just multiply by it. So you have cosine of 4x, that's the derivative of the outside, times the derivative of the inside, so times 4. Or you might see this written as 4 cosine 4x. Either way is fine, but I do the derivative of the outside, then I do the derivative of the inside, then I multiply them together. Let's do the next one really quickly, and then we'll get down and we'll do the rest of these examples. Here my outside function, right? It wasn't the cosine. The cosine was the thing that had something happening to it. You think, what is that something happening to it, right? What is that outer framework? Which for here, it was cubic, right? You were taking something and you were cubing it. So your outer framework is the cubic function. And I know the derivative of something cubed would be 3 something squared. And then whatever was inside, whatever was getting cubed, stays on the inside, and now it's getting squared. So I have 3 cosine squared. So now I've accounted for this. And now I need to multiply by the derivative of the inside, and I know the derivative of cosine is negative sine. So I do the derivative of the outside times the derivative of the inside. I find each piece's derivative, then I just multiply them together. And then you could rewrite this as negative 3 cosine squared sine of x, right? Just bring the negative to the front. The coefficient was all the front. You still have the cosine getting squared, and then the sine was just linear. So you just identify all of the different layers of the composite, and then you just multiply. You find all their derivatives, then you multiply them together. It's weird, right? It's the hardest rule, not because of how difficult it is, but just because of how sneaky and how kind of tricky it is, right? If you can remember to do it, most of the time you will do it correctly, but the truth is most students miss points with chain rule frequently because you just miss it, right? You forget to do it. You just don't see it on the page. So make sure you can recognize when something is a composite, what the different layers of that composite are, because chain rule is just going to require you to take all of the derivatives of all of those pieces and then multiply them together. Okay, let's keep practicing, right? Best way to get better is just to practice. Always just identify the layers if you need to, then take the derivatives of each one, multiply it together. Here we go. I've got this outer framework, which is something to the 5th power, and then I've got that inner piece, which is 4x cubed plus 3x minus 2. If you need to, you can kind of write this decomposition. You can kind of decompose it and show what the individual layers are, right? I've got the outer function, the outer framework, then I've got the inner function, that inside piece. I just have to identify them, take the derivative of each piece, and then multiply those derivatives together. That is what chain rule tells us to do. So let's go for it. The derivative of something to the 5th power would be 5 something to the 4th. And then whatever was inside, right, whatever was getting raised to the 5th, I'm just going to copy, and that same thing is being raised to the 4th, right? So I've done the outside derivative, right? The derivative of something to the 5th is 5 something to the 4th, and now I need to account for that inside function by taking its derivative and then multiplying by it. So here we go. That looks like 12x squared plus 3. Make sure you put it in parentheses. And then you can just stop. You don't have to multiply it all out. You can just stop there. That's fine. The derivative of the outside, remember here, a lot of times if you don't write it out, this is kind of what I do. I see I've got stuff to the 5th power, so that derivative would be 5 stuff to the 4th. Then you just copy, and then you actually account. Hey, what is the derivative of the inside piece? You account for it by just multiplying by the derivative of that inside piece. But you've accounted for both layers. You're done. Okay, next one. I've got something getting raised to the 2/3 power, and then that inside piece is x to the 4th plus 2. So I'm recognizing that it is a composite, so I'm going to have to do chain rule. That's the hardest thing. Actually doing the rule isn't too bad. Recognizing when to do it is the harder thing. All right, so here we go. I got something to the 2/3 power. So I've got 2/3 something. Ooh, 2/3 minus 1 would be negative 1/3. So that's your outside function's derivative. Remember, you still have to fill in something for that parentheses. And it's not going to be 4x cubed. Like, you don't do the derivative of the inside piece. This should not be 4x cubed. You are going to have a 4x cubed, but that 4x cubed, you actually multiply by it, right? You do the derivative of the outside, in which the inside should stay the same. And then you multiply by the derivative of that inside. Don't get greedy. Don't do it all at once. You do the derivative of the outside, then you do the derivative of the inside. Okay, and if you wanted to rewrite this, let's see, you could have an 8x cubed. You have a 2 and a 4. That's how I got the 8. Then you have a 3 on the bottom, and then this chunk, since it's got a negative exponent, you could move that cube root to the bottom. Or you could leave it like this. That's fine, right? The question just said find the derivative. It didn't say simple. Well, actually, I guess it did. It says don't leave negative exponents or complex fractions. I don't care, right? A lot of the times on the homeworks, you'll see this. I really don't ever care. You're fine to just leave it like this. And you'll probably notice that a lot on my answer keys. But derivative of the outside, that was this piece. Then I need the derivative of the inside. That was that piece. Just make sure you account for all of the different layers of that composite. Okay, here I'm going to rewrite it first. I've got negative 7, and then I've got all of this stuff to the negative 2nd power, right? And then here that inside piece, 2x minus 3. So this one is a composite. Your outer framework is negative 7 something to the negative 2nd, and then your inside piece is your 2x minus 3. So this is just a 2-layer composite. We're going to get a little bit more complicated here on the next page, but for now, just 2 layers. So I need the derivative of the outside. So this negative 2 multiplies down to the front. I'm going to have a 14 something to the negative 3rd power, right? That derivative or that exponent multiplies to the front, then decreases by 1. So I've done that. Now whatever was inside, I'm going to copy 2x minus 3. And then I need to account for the derivative of that inside piece, the thing that I just copied and filled in. I need to take its derivative. I don't put the derivative in the parentheses. I'm going to multiply by that derivative, which here was just 2. Okay, so there you go. And if you wanted to rewrite it, 14 times 2 is 28. And then you could put that chunk as being cubed on the bottom. Again, I don't really care if you simplify it. It doesn't really stress me out one way or the other. Whatever makes you feel all warm and fuzzy. Okay, so chain rule, it's a little bit tricky. Derivative of the outside times the derivative of the inside. That's generally what you have to do. Just make sure you can identify all the different layers of that composite, and then just multiply the derivatives of all those layers together. Okay, next one looks a little bit nasty because you have a quotient rule, right? You've got division, and then within the quotient rule, you've got a chain rule. Okay, so this is about as complicated of a derivative as we're going to see, but we still should be able to do them after knowing the quotient rule and after knowing the chain rule. So let's practice. I'm just going to rewrite this very quickly because I hate cube roots. It's 5x on the top, and then I have an x squared plus 2 to the 1/3 power on the bottom. I just like the 1/3 power more than I like the cube root. I just think it looks a little bit nicer. Okay, so this one's going to be a little bit complicated. I would definitely recommend you would take notes over this because it's probably as tricky as we're going to get this year, but try to pay attention. Okay, remember quotient rule. You need the derivative of the top, which is not going to need chain rule, right? The derivative of the top is really easy. Derivative of the top times the bottom. Then I'm going to minus, and then the derivative of the bottom, right? Since I've got this piece being raised to the 1/3 power, the derivative of the bottom is going to require chain rule. So the derivative of the top is easy, no chain rule, times the bottom, you just copy, that's easy, minus the derivative of the bottom, that's where the chain rule is going to be within the confines of this whole quotient rule, and then times the top over the bottom squared, right? So just be careful. Let's do it. The derivative of the top is easy, it's just 5. Times the bottom, that's easy, I'm just going to copy. All right, so the derivative of the top times the bottom minus, now I need the derivative of the bottom times the top. I'm just going to copy the top first. Right, so I have the derivative of the top times the bottom minus, I haven't done the derivative of the bottom yet, but we're about to, times the top, and then that's all over the bottom squared. So I'm just going to do the rest of it. If you take that denominator and then you square it, it's going to be something to the 2/3 power, right? So I'm just going to leave it like that. Okay, so I still need to do the derivative of the bottom. You've gotten most of this quotient rule done. You did the derivative of the top times the bottom, so you just copied, minus, you need to do the derivative of the bottom, times the top, so I just copied, and then over the bottom squared. So we've got a lot of it, but now I just need to do the derivative of this piece right here. And you see, hey, this piece, right, that's going to involve chain rule. You've got something to the 1/3 power, and then you've got what that inside something is. So you just have to account for both of those layers, take both of those derivatives, and then multiply them together. Okay, so let's go for it. Here we go. The derivative of something to the 1/3 power would be 1/3 something to the negative 2/3. And then whatever was inside stays inside. So now I've accounted for that layer. How wonderful. And then I need to multiply by the derivative of that inside piece, which was just 2x. Okay, so you had the derivative of the top times the bottom minus. All of this was the derivative of the bottom. That's what involved the chain rule. Times the top. All of that's over the bottom squared. Okay. Again, I'm not going to simplify it. You can look on the notes key, the PDF version, if you want to see how it simplifies a little bit. There may be a mistake on that notes key, but this is fine. Derivative of the top times the bottom minus derivative of the bottom times the top over the bottom squared. So kind of an ugly answer. Oh well, sometimes we get ugly answers. Okay, now all these ones, all this box says next is like, hey, chain rule is going to work whenever you have trig. Like if you've got sine of stuff, your derivative is going to be cosine of stuff. And then all this is telling you to do, that du dx, that's just telling you to do chain rule. That's telling you to do the derivative of the inside piece, right? If that inside piece is u, you need to take the derivative of u with respect to x. So all that du dx is telling you is to multiply by the derivative of the inside. It's telling you to do chain rule. So let's practice. Okay, here I've got cosine of 3x, and I know the derivative of cosine is negative sine, so I'm going to have negative sine, and then whatever was inside of the cosine is still inside of the sine. You should never, ever, ever change the argument of the trig, right? Don't change what's inside. Now you need to account for the argument. You have to do the derivative of the inside, and you're just going to multiply by it. So here you would see this derivative as written, negative 3 sine 3x. The derivative of the cosine is your negative sine 3x. That's the outer framework. And then that 3 is there because of the chain rule. It's telling you to do the derivative of the inside. Okay, the next one, I've got sine of stuff. And I know the derivative of sine of stuff is cosine of stuff. Now, again, be careful. What goes inside? Is the inside going to stay 5x squared, or is the inside going to change to 10x? Because the most common mistake is when students try to either just forget it, or they try to do too much, and they put the 10x inside. No, you do one derivative at a time. I'm doing the derivative outside, in which the inside piece stays the same, right? The derivative of sine is cosine, and whatever's inside stays inside. But now you have to account for that inside piece by taking its derivative. And you can either stick it at the front or you can stick it at the end. I usually will just write stuff in the front, right? So 10x cosine 5x squared, that's your chain rule derivative. You have the derivative of sine, that's your cosine. Then you have to account for what that inside stuff was. So multiply by the derivative of the inside. Okay, the next one is cosecant. I know the derivative of cosecant is negative cosecant cotangent. So I've got negative cosecant cotangent. And then whatever was inside stays inside. So 7x to the 5th, 7x to the 5th. So now I've done the outside framework, right? The derivative of cosecant is negative cosecant cotangent. Both of those arguments, you just fill in with what the original trig was. And then you have to think, okay, as I copy that inside stuff, what is its derivative? Well, 5 times 7 would be 35. So I'm going to have a 35 x to the 4th, and that's going to kick out to the front because of the chain rule. Okay, hopefully that's all right because it's about to get a little bit harder. On this next example, we're going to not just have a 2-layer composite, we are actually going to have a 3-layer composite. That's okay though, we can still do this derivative. You just identify all the different layers, take the derivative one piece at a time, multiply all the pieces together. So let's go for it. First thing I would recommend is you could rewrite this as cosine of 5x, and then all of that's getting raised to the 4th power. That kind of just helps you see what the decomposition is going to be, right? Just rewriting it. Instead of having cosine to the 4th, which kind of looks like the cosine's the outer function. No, the 4th power, right? That's the outer framework. So really here, rewriting like this helps you see the outer function is I've got something to the 4th power. Then that middle layer is the cosine. And then that innermost piece is what's inside of the cosine. So this is really a composite that's 3 layers deep. You have the outermost function, which is something to the 4th power. Then you have that that middle piece, which is a cosine of stuff. And then you have that innermost piece, which is what the innermost stuff was, the 5x. So this one's a little bit weirder because you got an extra layer. That's okay. This one just means take the derivative of all 3 of those, multiply all 3 of those derivatives together. Chain rule is not hard. It's just a little bit tricky because it relies on a lot of pre-cal skills. So let's go for it. Something to the 4th power, I can do that. 4 something cubed, right? That's easy. I can take the derivative of something to the 4th power. And then whatever was inside, whatever was getting raised to the 4th, you just copy. And then that same thing will be now getting raised to the 3rd. Okay, so you're done with that part. Wonderful. Now just move on to the next one. The derivative of cosine of stuff is going to be negative sine. And then whatever was inside of the cosine goes inside of this sine. And now you're done with the middle layer, right? You're just doing one derivative at a time, and then you're just multiplying by all those derivatives to get them all together. And then the last one, that innermost piece was a 5x. I know that guy's derivative is just 5. And then so there you have it. You could rewrite it if you want, but that is a pretty good way of writing that answer. If you wanted to, let's see, you have a 4 and a 5, so you'd have a 20. You have the negative, and then you could rewrite it as cosine cubed, and then sine 5x. So that's probably how your answer would look with everything just as simplified as much as possible. But the 3-layer composites, you just identify what the 3 layers are, take the derivative of each one, and then you just multiply those 3 derivatives together. Even if the composite was like 10 layers deep, you would just break it down, identify the 10 different layers, take those 10 different derivatives, and then your answer would be long, but it wouldn't be really hard. You would just multiply all of those 10 different derivatives together, and then you link them all together, right? The chain rule, right? All those derivatives are linked together. Okay, next one. Here we go. I'm going to rewrite it. You have something getting squared, and that inside something is a secant of 4x cubed plus 5. Sorry, I started writing that really small. But hopefully you can see the decomposition. You've got the outer framework, which is something squared. And then you have that middle function, which is the secant. And then you have that innermost piece, which is the 4x cubed plus 5. So this one's a 3-layer composite. We don't usually get any harder than a 3-layer composite. And even then, most of the times it's just going to only be the 2. Occasionally we have to do the 3. Most of the time 2, but we need to be able to stretch out to 3. It's not going to get harder than 3 in this class though. Okay, so I identify all the layers. I'm going to take their derivatives, multiply all them together. So here we go. Something squared. I know the derivative of something squared is just 2 times something. Right? That's easy. The derivative of something squared, that 2 just multiplies to the front. It's 2 something. Now, whatever was inside getting squared, that same thing is still inside. So I've got secant of 4x cubed plus 5. So I'm done with that outermost layer. Let's move on. The derivative of secant, look up here in your box, the derivative of the secant is secant tan. So here we go. The derivative of this middle layer, the derivative of secant, oops, I should have given myself more room. The derivative of secant is secant tan. And then whatever was inside of that secant, which hopefully you gave yourself more room than me, you just copy down 4x cubed plus 5, 4x cubed plus 5. So we had the derivative of the outside, which was something squared, so it's 2 times something, and that one was done. Then we had that middle layer was a secant. The derivative of secant is secant tan. Copy down whatever was inside, goes inside both. And now I need to account for the derivative of that innermost piece. The derivative of this would be 12x squared. And then I just throw that all the way at the end. So I just identify what the different layers are, take all of their individual derivatives, multiply them all together to link them. Right? Now if you wanted to, you could have rewritten this. You have a 2 and a 12, so that's a 24. X squared. Then you'll see you have a secant times a secant. So you could regroup this as secant squared, 4x cubed plus 5. And then you only had the tangent once. So that's generally how your answer would look. Again, the reason why that's secant squared is because you had a secant, and since those arguments matched, those are like terms, and you can regroup them as a secant squared. Okay, next one. Here, my composite is I've got a tangent of stuff, and then that inside stuff is sine of x. Okay, so your outer framework is the tangent. The inner function is the sine. It's weird that you have trig in both layers. That's atypical, but it could happen. Let's do it. The derivative of tangent is secant squared. So there's your derivative of the outside function, and then whatever was inside of the tangent, that's going to be inside of the secant squared. So since there was a sine inside of the tangent, you're going to have a sine of x inside of the secant squared. Remember, those trig derivatives you need to know. The derivative of tangent is secant squared. Okay, now that outside layer's done. Now I just need to account for the inside piece. The derivative of sine is cosine. So notice, it wasn't a cosine that went in here. You would just multiply by that cosine. You multiply by the derivative of the inside. And then nothing's going to cancel here. That's as good as it's going to get. The secant doesn't reduce with the cosine because the arguments are different. Okay, now the next one is kind of similar to stuff we did at the very end of the product and quotient rule, where it doesn't actually give me the functions. It doesn't tell me what the individual layers are. It just says, hey, H is this composition. It's f of g of x. And then it just kind of gives me this list of information. Okay, sometimes it may be given to you in a list. Sometimes that information may be given to you in a table. Sometimes it may be information that you have to pull from a graph. But we should be able to do these. These are actually deceptively easy. Questions like this are much simpler than what we've been doing, right? You just got to know the derivative rule, take the derivative, and then just go snag the information from however it's presented to you. So let's go for it. First thing is to write out the derivative. So if you have h and you want to get to h prime, take the derivative. That's going to involve your chain rule here. Your outside framework is f, and then your g of x is your inside. So I know if I have f of something, I need to do f prime of something, and then whatever was inside stays inside. So it's f prime of g. And then you are going to have a g prime, but the g prime is not in there, right? It's not f prime of g prime. That's trying to be too greedy and trying to do all of it at once. You have the derivative outside. Since the outside's f, the derivative of it would be f prime, and then whatever was inside copies. And then you need to account for this by just multiplying by your g prime value, right? So your derivative of the outside, in which the inside stays the same, and then you multiply by the derivative of the inside. And then here it specifically wanted us to plug in 3. Okay, so now let's go through. We've done all the calculus. Now everything else is just straight up algebra and arithmetic. I need to do, let's do this left chunk first. I need to go get what is g of 3, and then whatever this number is, I need f prime of that number. I don't need f prime of 3, right? I need to figure out what is that. And then once I know that number, I need f prime of that number, right? This one's 2 steps. Okay, so first thing, let's go get g of 3. Look at the list. It says g of 3 is 4. Okay, now I need f prime of 4. So now I go to your list. F prime of 4 is 8. So that left chunk is 2 steps, but that left chunk ends up ending up as an 8. Ends up ending up. That's repetitive. Okay, I'm sorry. Now this other piece is easier. It's just 1 step. You need g prime of 3. So let's go find it. Let's see. G prime of 3 is -5. And then you're done with that piece. So then we get the answer was -40. But the composite ones, you just got to be careful. A lot of the times what I see is like, I don't know, people just mess up on this left side. This left side is just 2 steps, right? It's not hard. You just need to do the inside first, figure out what that number is, and then you do f prime of this new number, right? So sometimes you may have a little bit of extra information. Just always be careful. Just write out your derivative rules. Just do it one thing at a time, and you should be okay. Okay, let's see. I guess we can go a little bit farther. Yeah. Sure. Let's at least do these. Yeah, let's just finish probably this page. Okay, so some more chain rule questions. Again, just identify the layers of the composite and then take the derivative of each one. Here we go. I'm going to rewrite it. Not doing any calculus yet. I'm just rewriting it. I've got 4x squared plus 7x. All of that is being raised to the 1/3 power. So your outside framework is something to the 1/3 power, and then your inside piece is that 4x squared plus 7x. So if you need to do this decomposition stuff, please, by all means, please go for it. I will probably stop doing it. If you look at the homework keys, I may have it, I may not, I don't remember, but I'm probably going to stop doing it, at least in the notes. But I just need to take these 2 derivatives and then multiply them together. Here we go. If I got something to the 1/3 power, that's 1/3 something to the -2/3. And then whatever was inside stays inside. So I've got 4x squared plus 7x. Now I'm done. I've accounted for that outside framework. That's good. Now I need to account for the inside piece. The derivative of this inside piece, make sure you put it in parentheses. Looks like it's going to be 8x plus 7. And you can just leave it just like that. That's fine. Again, I don't really care. I don't care. The next layer, or the next example, sorry, actually both of the next 2, they're going to be 3-layer composites. That's okay. Remember, you could rewrite this as a sine of x cubed all to the 4th power. Since the sine, a lot of the times instead of having that 4 attached to the trig, I like to rewrite it because that kind of helps me see, hey, that outer framework is not the sine. The outer framework is something to the 4th power. That middle layer is the sine. And then that innermost piece is the x cubed. Again, rewriting it is just my personal preference because I think that helps me see what all the decomposition, what all the layers are going to be. If it doesn't help you, you don't need to do it. Okay, here we go. The derivative of something to the 4th power would be 4 something cubed. And then whatever was inside getting raised to the 4th, that same thing is inside, now getting raised to the 3rd. So that layer's done. Move on to the next. The derivative of sine of something is cosine of something. And then whatever was inside of the sine is now inside of the cosine. And then that layer's done. And then the last one, the derivative of that innermost piece, 3x squared. There you have it. And then the last one, again, it's another composite. That's 3 layers deep. You have something getting raised to the third power. Then you have your tangent of something, and then you have that 5x. Just try to do this one without writing all the compositions, right? Just see if you can visually identify what the layers are. You've got something getting raised to the third power, and I know the derivative of something to the third power is 3 something squared, right? You've got something to the third power, the derivative is 3 something squared, and then whatever this was, you just copy. So tangent of 5x. So I'm done with the outer framework, right? I'm done with the something to the fourth power. So that's great. Now let's move on to the next layer, which was the tangent. And I know, or you should know, the derivative of tangent is secant squared. And then whatever was inside of the tangent is still inside of the tangent's derivative. So again, something to the third power, that's accounted by 3 something squared. Very good. Then you have the tangent, that's accounted by the secant squared, and then we still have to account for that innermost piece, and the derivative of it is just 5. So even the ones that are 3 layers deep, right? You just need 3 derivatives, and then you just multiply them together. It's not terribly complicated. It's not impossible. If they're just sneakier, right? So just be careful. Let's do 2 more, and then I'll stop, and then we'll finish this notes bracket. Actually, no. I'm going to stop right now. We'll pick up with the next example in the next video.